So we see on this simulation, it shows that green dot, that would be that point P. It goes perpendicular to the direction of the wave. While the wave is going to the right, the motion of the particles go up and down. So that point P would need to go up as this wave is moving to the right. Now we're going to get to the velocity of this wave. So we're being asked also to calculate the velocity of the wave. So in that wave, it was given that the frequency was 6 hertz and the wavelength is 3 meters. So what we're being asked to use is that wave equation that we were looking at yesterday, that this v equals to f times lambda. So in order to calculate the wave speed, you have to use, well, the frequency, that's that hertz. And so whenever you see hertz, that hz, that's that frequency. So I know the frequency here is going to be this 6 hertz. And the wavelength, that's the distance of the wave for one complete cycle. That's 3 meters here. And so I know that 6 times 3 is going to be 18. So I know I'm going to get that my wave speed, which is this velocity, is going to be 18. That's the number. But I know hertz. So I know hertz is inverse seconds because that's how many cycles per second. So we're going to have 6 cycles per second. So 6, 1 over seconds, times 3 meters. 6 times 3 is still 18. Meters times seconds gives us meters over seconds. So it gives us the velocity that we expect in terms of units in meters per second. And we also get the quantity, the magnitude of that velocity as well. So we have the velocities being 18 meters per second. And it's going to the right, so we can say that this is a positive velocity as well. So we have now that as what we're doing. So now that we have the velocity of the wave, we have that wave speed, we can now go back to our unit 1 waves. And what we're going to start working on is going to be our pages 2 and 3 wave characteristics. So what I'm going to ask that we do is we wrote some notes yesterday. We took some information yesterday. What I want you to try to do right now is we're going to label up the parts of our wave here, where there's part A, B, C, D, E, F, G. A, there's a B, there's a C, there's a D, E, F, and G. I want us to try to label this graph as best we can. And then I'm going to bring us all back together so that way we're going to be able to work on this together. So what I want you to try to do right now is I want you to do this. So I'm going to pause my screen so that way you're going to be able to do A through G on number 1. All right, so bring it on back now. Bring it on back now. So I tried to label mine as well to where some of these terms are reused. So that letter A, that is the peak, it's the crest, it's the topmost part of the wave. Then getting to letter B, this is that wavelength. That's that repetition. That's one complete cycle of this wave. That wavelength also has a symbol, that upside down Y, that lambda. So I'm even going to write that over here next to it. That lambda is the wavelength. And we also see here at letter C that we have an amplitude going from the equilibrium mark up to the crest, up to the peak. That is the amplitude. And letter D, this is the trough. Letter E is also the amplitude going from the equilibrium down to the bottommost part of the trough is the amplitude. Letter F is also a wavelength. That's one complete cycle of a wave. And this letter G, this line right here is that equilibrium line. If no one is shaking the rope, no wave is going through the rope. If no work is being added to that system, then there's no energy there to transfer along this wave. And it would be all at the equilibrium mark along the wave. So that takes us here down to these fill in the blanks. So waves they carry energy from one part to another. If there's no energy going through the wave, or going through the rope, going through the medium, then the wave would be here at this equilibrium. It would just stay still. The highest point in this transverse wave, this is known as that peak, the crest, while the lowest part is the trough. The amplitude is the height of the wave. And the distance from one crest to the next is the wavelength. I also like to write that upside down Y, the lambda, just because I like to know that symbol. I like Greek letters, it's fun. So now I know that the wavelength is, I know the amplitude. I'm now going to come down here to number 6, where we're going to compare some waves. So we see I have these waves going up, down, and up. And I have this going down, then up, then back down, and all this over here. So what we got to try to do is we got to try to figure out the number of complete waves. So one complete wave is just one complete cycle. So green probably isn't the best one to draw in. Or red, because now it looks like I'm trying to make a Christmas wave. But this is one complete cycle. If I were to break this down, I could break this into parts where I have 1/2 of a cycle. I can get to 1/4 of a cycle. And what I see here over this entire wave is I have one complete wave plus a half. So I have 1.5 waves here in this cycle, or in this series. And then for this next one, it goes down, then back up, then back down to here. So in this one, we have one complete wave. Then as I get to letter C, it goes up, down, back to up. So this is one complete wave. And then from here, going up, down, back to up, I have another complete wave. And then this goes up and down. So here I have 1, 2.5. So I have 2.5 complete waves then for this letter C. And then letter D, well, this is half a wave because I could take this plus the other half to make one full wave. But this part right here is just the half a wave. So this is half of a wave. Oh, yes, please. You could do 1.5 lambda, 1 wavelength, 2.5 waves, and half a wave here. Anytime we can label up and be more specific about what it is that we're saying, it's always better than not being more specific. So yes, if you can label it better, be more precise, then do so. So as we continue on here on this number 6, we're looking for which one of these has the biggest amplitude. So the biggest amplitude, that's going from that equilibrium mark. So it's a little hard to tell on mine because I've just drawn over mine. But the amplitude from B to C, that's this height. I could draw the amplitude or the equilibrium mark. But if we look at these equilibrium marks going from here to here and here to here, it looks like B and C, they're about the same. D maybe a little bit more than B and C. And what I see going for letter A is it looks like going from letter A, we get a much bigger amplitude. So it looks like letter A has the biggest amplitude. And now we're going to look for the shortest wavelength. And that's going the distance here to here. This is 1 wave. And going from here to here, this is 1 wave. Going from here to here, that's 1 wave. And going from here all the way over there, that's 1 wave. So I can already tell just by my rough drawings that it looks like letter C has the shortest wavelength. So it looks like letter C is the shortest, and then letter D looks like it has the longest wavelength. So now we have a good comparison between some waves. Now we're going to get down here to number 7. We're going to express into words and mathematically to express the relationship between period and frequency, wavelength and frequency, and wavelength and period. So what I'm going to do, take us up here. We already have a relationship between period and frequency. And we have this relationship here between wave speed, wavelength, and frequency. So we have some stuff on this. We already wrote a little bit of notes about these two and the relationship that they would have with respect to one another. So we do know that this period, which is denoted with the letter T, is equal to the inverse of that frequency. So you could say that frequency and the period, they are inversely related. So for the next one, we know V equals to F times lambda. Wave speed is constant in a given medium. So constant number equals to these two things multiplied by one another. So if a constant number equals to two things multiplied by one another, so that tells me that as frequency increases, wavelength decreases. As frequency decreases, the wavelength increases. So what we're seeing once again is that this frequency is proportional to the inverse relationship of the wavelength. Or we could say that the wavelength is proportional to the inverse of the frequency. Now, this looking fish type of thing is me saying proportional, because a frequency does not equal to 1 over the wavelength. 1 over meters is inverse meters, not hertz. So that's proportional, not equal. So there's a difference here. So we do know that this wavelength is proportional to this inverse frequency. So we can say once again that frequency and wavelength now they are inversely proportional. So it's key to add in that it's proportional to one another, not just that they're equal to one another. Because the wavelength meters does not equal to seconds. Well, then, if we see that the period equals 1 over the frequency, and if we know that this wavelength is proportional to the inverse of the frequency as well, then it kind of says that this wavelength is proportional to the period. Wavelength proportional to the period, the time it takes to complete one cycle. So wavelength and period they are directly proportional. All right, so now that we have the mathematical relationship between some terms, we've kind of looked at these different terms as we label them on these graphs. We've tried to apply them to say, well, here, this one has a bigger amplitude, this one has a shorter amplitude, this one has a bigger wave, longer wave, and then we compared period, frequency, and wavelength, and we tried to say, well, how are they related to one another? As we continue, now we're going to use and apply that wave equation. We're going to start here with this number 8. It's going to have a wave generator that's going to produce 10 oscillations per second. So here for number 8, we're getting that the frequency generated is going to be 10 oscillations per second. So 10 oscillations per second. And the speed of the wave is 300 centimeters per second. So this wave speed is 300 centimeters per second. And what we're trying to find is the wavelength of this wave. So that's what we're going to try to first find. So what we need to find is this wavelength. That's what we're trying to find here. So what we need is our wave equation. So starting off with this, V equals to F times lambda. This is the wave equation we're going to use. And we also need to recognize what it is that we're dealing with. Because this frequency, we're not going to be dealing with oscillations per second. We're going to be dealing with hertz. And that's the number of cycles per second. Well, one oscillation is one complete cycle per second. So we're dealing with a frequency of 10 hertz. So I don't need to do anything with my frequency, but my velocity here is in centimeters per second. We need to get this to meters per second. So that way we can use our wave equation of V equals F times lambda. We need it to be in those units, just like as we wrote out yesterday. So if I know my velocity is 300 centimeters per second, I need to get rid of the centimeters and get to meters. So I want meters on top. I'm gonna get centimeters on bottom, so my centimeters cancel out. There's 100 years in a century. There's 100 centimeters in a meter. So there's 100 centimeters in 1 meter. So then it's gonna be this 300 divided by 100. So it's gonna be 3 meters per second. 3.00 meters per second. And I'm keeping the 3 significant digits because it was written out that it had 300 and then there's that decimal point. So that decimal point made it so that way I have 3 sig figs here. And so I'm going to keep the 3 sig figs as I try to follow along. The frequency does only have 1 significant figure, but we're not going to get into this in depth into that. But now that we have that, we're trying to solve for the wavelength. So I need to solve for my wavelength by dividing by my frequency. Frequencies cancel out, giving me wavelength is my velocity or my frequency. I know my velocity in terms of meters per second, so I have 3.00 meters per second, and I'm going to divide by the frequency of 10 hertz, which is also inverse seconds, so the inverse seconds cancel out, giving us just meters. So 3 divided by 10 is 0.3. And since this is 1 sig fig, I could write out more, but I'm just going to keep this as a 0.3 meters. So our lambda is a 0.3 meters. So the wavelength lambda is this 0.3 meters. And I got to show my work. So I wrote it down on this separate sheet of paper so that way we could all see it and we can read through it. And I wrote more than I needed to. So that way we could understand where I got to. For you, you need to show your work of how you get to your answer of a lambda being 0.3 meters. And now we're going to get to this relationship here. Well, what's going to happen to the wavelength if the frequency is increased? Oh man, there's a lot of math I could do here. I could go back and I could look at some stuff, but I also wrote out some stuff about this. So we're saying now the frequency is going to be increased. Well, we said that the frequency and the wavelength are inversely proportional. So in other words, as this frequency is going to increase, then the wavelength will decrease. So what happens to the wavelength if the frequency is increased? Well, the wavelength, lambda, will decrease. It will not just decrease, but it's going to decrease proportionally. What that means is if the frequency is increased by double, by 100%, or rather, if you double the frequency, then you're going to cut the wavelength in half. If you get 4 times the frequency, you're going to have 1/4 the wavelength. If you're going to have 18 times the frequency, then you're going to have 1/18 of the wavelength. So it's going to decrease proportionally. So now we're going to continue down here to number 9. So here at number 9, I'm going to do the same thing where I'm going to draw this out on a separate sheet of paper so I have more room to write so you can all see what I am writing out here. But we have a wave on Beaver Dam Lake, and it's going to pass by 2 docks that are 40 meters apart. So this is where I'm going to draw this out. So here for number 9, I'm going to draw out, I have 1 dock here, and I'm going to have another dock here, and they're separated by 40 meters. It's 40.0 meters if I wanted to be specific. They're separated by 40 meters. And what we see is that we're going to have a crest at each dock. So at each dock we have a crest, and I got a crest here at this dock as well. So there's a crest at each dock, I got that. And there's another 3 crests between the 2 docks. So you're standing here on this dock, you see there's a crest, We're also gonna have 1 more crest, 2 more crests, and 3 more crests in this. And what we're gonna try to do is determine the wavelength. But what we see here is that we're gonna have this to here, to here, and to here. Yes, this is not a perfectly drawn looking wave. I just drew it out as I read it. So now what I see is I have going from here to here, that's 1 complete wave. That's 2 complete waves, 3 complete waves, 4 complete waves. So I have my lambda is going to be 40 meters. That's the total distance. And I'm going to divide it by the complete number of waves. So I'm going to write this out so we have an idea of what I'm doing. So I'm going to have the total distance and I'm going to divide by the number of waves. So the total distance here is 40 meters, and the number of waves was 4. So 40 meters divided by 4 still gives us meters, which is good for wavelength. We have 10 meters for our wavelength. So lambda is 10 meters. So you really needed to draw this in order to get to this part here. So once again, you got to show your work. Lambda is 10 meters. Show work of how you got to it. I really doubt that anyone's going to be able to read this and be able to automatically infer that, well, with 5 crests, you get 4 waves. So you need to really draw this out and show your work of how you're able to get to it. You can't tell me that you really can just read and say, well, there's 5 crests, so that makes 4 waves. No, you need to really draw this out, say, well, you have an understanding of what it is that you're doing. So now we're going to get to this letter B, where we're going to have 10 waves are going to pass each second. Yes, you're going to be able to have some decimals for waves. So let's say, for example, in this one here, let's say we got 40 meters up to this part. Let's say that was 40 meters. If that's the case, then you're going to have 1 complete wave, 2 complete waves, 3.5. So then you would do 40 meters divided by 3.5. And yeah, I'm not going to do that in my head right now. Actually, I have a wonderful thinking machine. 40 meters divided by 3.5. We would get a 11.4 wavelength. So yes, you can have decimal waves, just like how we looked at in number 4 of this before. So we have 10 waves passing 1 dock in 16 seconds. So that's 10 complete cycles in 16 seconds. What we're going to try to do is determine the period and the frequency of this wave. So for 9B, we know the period is going to have units of seconds. Oftentimes, just writing out the units of what it is will help you get to what it is that you're trying to solve. I know frequency has units of hertz, and a hertz isn't just doing physics work, but it's inverse seconds. So inverse seconds for frequency, and the period is in regular seconds. So we know that we have 10 complete waves in 16 seconds. So we can get to the period. The period here is going to be the amount of time divided by the number of waves. And it's not just the amount of time, this is the total time. The total time divided by the number of waves. And that will get us to the period here. So in this case, we're going to have 16 seconds divided by the number of waves, which is 10 waves. So seconds divided by nothing is still seconds. So 16 on 10 is 1.6 seconds. So we get our period as this 1.6 seconds. From here, we could use that relationship that we know that frequency is the inverse of the period. So we could use that the frequency is 1 over the period. We could also use that it's the number of complete cycles, the number of waves, divided by the total time. All will get us to the same thing. So in this case, we had 10 waves over 16 seconds. So the number of waves over seconds, number of cycles per second, that will get us to hertz. And 10 divided by 16 is a 0.625, 0.625 hertz. And we can also check what is 1 over 1.6. Oh, good, it's still 0.625. So we know the period and we know the frequency of our wave. 0.625. Ouch, that hurts. So once again, on your paper, I want you to show your work of how you got to your solution, how you got to what you got. So we have the period and the frequency of 1.6 seconds and a 0.625 hertz. And show that work, show that work. So lastly, now we can get to the speed of this wave. So the speed of the wave is v equals to f times lambda. We know the frequency, it's at 0.625. We know the wavelength of 10. So this frequency is a 0.625, ouch, hertz, times the wavelength. I don't keep it 100, I keep it 10. So then we get this velocity is a 6.25 meters per second. And that's showing my work. That's doing enough. I'm saying the equation I'm using the numbers with units, and then I'm circling my answer. So this is me showing my work. You can't just say, well, it's 0.625 times 10, and that gets you to somehow meters per second. And you can't just multiply two things because, well, why not divide them? Why not add them together? Why not divide them? Because no, you're doing v equals to f times lambda. That's what you're doing. You're not just adding things, dividing things, and you're just taking numbers, putting them together. No, you're taking the frequency times the wavelength. So state the equation that you're going to use. So this is going to take us down here to number 10. So with number 10, we're getting that the sound wave, the wavelength of a sound wave in the room is 1.13 meters. So we know that this wavelength is a 1.13 meters. And we know that the frequency is a 301 hertz. What we're being asked to find is first, this letter A, I want us to find the speed of the wave in the room. So you can use that wave equation, that V equals to F times lambda again. Then we're going to double the frequency of the wave. When you take this frequency and you're going to double it, what's going to happen to the wave? The wave's speed, rather. I want us to note that you're going to be working in the same medium. The medium does not change. Then, what happens to the wavelength if you cut the frequency in half? So then we're going to take this frequency and we're going to go to half of it. And what's going to happen to that wavelength? Once again, we're in the same medium. The medium did not change. And that's going to be where I leave you off. So I think you guys got a good start to get to this number 10, where you're going to have to calculate the wave speed. Here, I want you to think before you calculate. It's a real easy calculation, but I want you to think before you calculate, because we're working in the same medium. It's a constant medium. The medium did not change. So I'm going to even do something here. Ooh, I'm highlighting it. Maybe that makes it important. So then next, what happens to the wavelength if you cut the frequency in half? I'm not going to highlight the same medium because we have an understanding what should be happening with that frequency. So on that note, so do I have any questions from anyone here today about anything we just been talking about, talking at? All right, well then on that note, I'm gonna stop the share and I'm gonna say thank you to all of you for coming out. Yeah, good luck and I'll see you guys again tomorrow. Goodbye now. I will. You do the same now. Have a great day.